So in this question, we are given a subset of the real 2 by 2 matrices. And what we're first told is to prove that it's a subspace. So to prove it's a subspace, we need to do two things. We need to show that it's non-empty, and we need to show it's closed. And the reason why we need to show these two things is it's much faster to use the characterization by closure theorem than to prove all of the axioms, especially because you're proving closed anyway if you were to try to prove all axioms. So first thing we're going to do is we're going to show non-empty. And to show non-empty, we're going to show that something's in it. So consider 0, 0, 0, 0 as 0 plus 0 equals 0, 0, 0, 0, 0 is in T. Thus, T is non-empty. And this 0 comes from my first entry, whereas this 0 comes from my bottom right entry. Now what we're going to do is we're going to let C be in, because it's reals, my field is the real numbers. It's not just F, it's R. And X, Y be in T. Then X equals A1, B1, C1, D1, where B1 plus D1 equals 0, and Y equals A2, B2, C2, D2, where A2 plus D2 equals 0. Consider CX plus Y. This equals C, A1, B1, C1, D1, plus A2, B2, C2, D2, which equals, what I do is I convert this into a single matrix, because this is in fact a single matrix. It's going to be CA1 plus A2, CB1 plus B2, CD1 plus, or CC1 plus C2, and CD1 plus D2. Now what I want to do is I'm going to add the first and last entry to show that it's in T. So now I'm going to look at, consider CA1 plus A2 plus CD1 plus D2. CA1 plus A2 plus CD1 plus D2 equals CA1 plus D1 plus A2 plus D2, which equals C times 0 plus 0, which equals 0. Thus, Cx plus y is in T. Therefore, by the characterization of subspaces by closure theorem, T is a subspace. And I should probably write out these words, but I'm just doing this for shorthand. Now what we need to do is, once we have proven it, we need to construct a basis. Okay. To construct a basis, what we're going to do is we're going to connect being in the set T to being a spanning set. So A is in T if and only if A equals A, B, C, D, such that A plus D equals 0. So I've started with what it means to be in T. And now I'm going to use this to construct a system of equations. So this is if and only if A equals A, B, C, D, such that A, B, C, D is a solution to the system A plus 0, B plus 0, C plus D equals 0. Okay. Now that I have that system of equations, note that it's a single expression and the leading coefficient is 1. So this is a system equation in echelon form, which means I have 3 free variables. The basic variable is A, and the free variables are B, C, and D. So I'm going to let B equal S equal R in R, C equal S in R, and D equal T in R. Then A equals minus T. Thus, A, B, C, D is a solution. Thus, if A, B, C, D is a solution, then A, B, C, D equals minus T, R, S, T. Therefore, A is in T if and only if A equals A, B, C, D, such that A, B, C, D equals R or minus T, R, S, T, where R, S, and T are in the real numbers. And now what I'm going to do is I'm going to connect these two together. This is if and only if A equals minus T, R, S, T, where R, S, T, and R, if and only if A equals, and now I'm going to expand in the obvious way. So it's going to be R times 0, 1, 0, 0 plus S 0, 0, 1, 0 plus T minus 1, 0, 0, 1. So if it means that A is in T if and only if it's a linear combination of these vectors, if and only if A is in the span of the set 0, 1, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 1. Okay, now we were told to create a basis. We have created a spanning set. So this set here is a spanning set. We've shown it's a spanning set. We now argue it is linearly independent. And I'm going to leave that as an exercise. Now, use the set S that we created to determine the dimension. Here, S equals the set 0, 1, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 1. Thus, the dimension of T equals 3, because there's 3 vectors. This has to do with inner products, which we did not cover yet. Okay. The last question here is about a subset P with n elements. Prove that it's cannot be a basis. Well, the big thing here we need to do is we need to consider the set 1 up until n, or x to the, sorry, consider the set 1x, x squared up to xn, and we'll label this S equals show, or let's call this alpha. Show alpha is a spanning set as the cardinality of S is greater than the cardinality of alpha, and alpha is a spanning set by the dimension bound theorem. S is linearly dependent. Okay, so that's the one technique. The other technique, so that's A. B, what you need to do is you need A of elements in S. So A F1 plus B, or A1 F1 plus A2 F2 plus AN Fn equaling the 0 function, where AI is in C and Fi is in the polynomial, or is in the set S. And now what we can do is we can take this linear combination and apply both functions to x. So we'll get A1 F1x plus AN Fn x equals z of x. Now these are all polynomials of degree n. You can rearrange, and you will construct a system of n plus 1 equations. And this should go to n plus 2 because our number was n plus 2. So you'll create a system of n plus 1 equations with n plus 2 variables. This then has a non-trivial solution. Thus, linearly dependent. So you can either create a homogeneous system of equations that forces a non-trivial solution, or you can create a spanning set and use the dimension bound theorem. In both cases, you need to build something and verify something. You need to either build a homogeneous system of equations, or you need to construct a spanning set. You need to show that spanning set or show that it's a valid homogeneous system. And then you're going to use a theorem, either the dimension bound theorem or that if I have more variables than equations, I have a non-trivial solution.